Welcome to part two of the IAS Edexcel Physics Unit 3. So in our previous video, part one out of the two parts, this is the final part. But in our part one video, we looked at the Unit 1 uh, practicals. In this video, we'll be looking at the Unit 2 practicals, okay? So Unit 2 and the practicals that are highlighted. So let's start with core practical 4, which is determine the speed of sound in air using a two-beam oscilloscope, signal generator, speaker, and a microphone. So for this, what equipment will we need? Well, we need an oscilloscope. An oscilloscope basically measures it just shows you how the waves look like, and how they change. We need an oscilloscope. We need a microphone. So this will be connected to a microphone. We need a loudspeaker, which will be over here. And we will need musical instruments connected to this speaker. So like I'll put like a boombox or something, okay? Now, we also need a ruler. So what we will do, is we connect the microphone to the oscilloscope, like we've done in this picture, and we input the sound. So we make sound play sound here, okay? Sound waves will travel from here to here, and as they travel, the oscilloscope will pick up a reading. Let me draw this more clearly. The oscilloscope will pick up a reading. So it will look something like this, okay? Now, what we do is we check where that is and we move the microphone behind. So this is the initial position of the microphone, but we move the microphone to around here. Actually, what we do is we keep moving the microphone behind until this image is formed again. So the wave will move behind, it'll regress until it eventually forms the same initial diagram that we had, okay? So let's have this as stage 1A, this is B, this is C, and this is D. So when we move the microphone from A, at A it should look like this, okay? This is at A. At B, it picks it up a bit behind, so the diagram will look slightly different, and at C, it will also look a bit different. Let me just draw it like that, okay? And at D, so as we keep moving behind, we have to aim to get this initial diagram. And let's say at position D is when we finally get that initial diagram on the oscilloscope. So we stop the microphone at position D and we measure the distance moved. When we measure the distance moved, we can label that as one wavelength. That is one wavelength, that the distance moved, the distance moved is equals to one wavelength of the wave. And we use the equation V is equals to F lambda, where F is the frequency and lambda is the wavelength that we have D. V is the speed of the sound in the air, which is what this core practical is about, core practical 4. And your frequency will actually come from the signal generator. It should be known, the signal generator's frequency. So we input those two values and we get our speed of sound in air, okay? Now, why is it that this is equals to one wavelength? As you move the wave behind, this initial position captured and this final position, so this is A, this is B, this position B becomes position B here, and this becomes C. So it shows that it has moved one complete wavelength, okay? Now this isn't one wavelength. I should have just drawn it like this. That makes more sense. And even this should just be like this. So this is one wave. Then B moves backwards, exactly one wavelength, and it repeats the same pattern, which demonstrates that it's moved one wavelength, okay? So yeah, that's how we do it there. It should be known that at times when you're told to read an oscilloscope and you want to know the frequency, you do frequency is equals to 1 over time period. What is time period? Time period is the time it takes for one wave to move, okay? So this will be in this will be in a box form, like such, and they tell you find the oscilloscope's frequency of the wave. You take the distance from here till here, you find let's assume that uh, this is equals to 4 boxes. In reality, it's equals to 4.5 boxes, but let's assume it's equals to 4 boxes. Okay, you know what? Let's just take 4.5. So this is 1 box, this is 2 boxes, this is 3 boxes, this is 4 boxes, and this is the 4.5, 4.5 boxes. And what we will do is we will find the time of each box. Let's say this is 0.2, this is 0.2. So we'll do 4.5 times 0.2. Whatever we get, let's say we get x, we should, that is our time period, t, also known as the amount of time for one wave to pass through, and frequency is equals to 1 over t. So if you want to get frequency, you do 1 over t. Now let's move a bit more faster. That took so long. Oh, also one more thing. Since the exam for most people is tomorrow, your amplitude is the distance from the minimum to the maximum displacement. So this is your amplitude, okay? That's what we need to know. The higher the amplitude, the louder the noise. Let's say you have a wave with light that looks like this rather than this. That shows that this one has a higher pitch because it has a higher frequency. So higher frequency, higher pitch, okay? And higher amplitude. So higher amplitude meaning louder, okay? That's what we need to know from there. So that is everything on core practical. Oops, that's everything on core practical 4. Now core practical 5, investigate the effects of length, tension, and mass per unit length on the frequency of a vibrating string wire. Okay, so core practical 5 is essentially investigating the effect of tension. Okay, so what we need for this, I don't know what's that now. Okay, core practical 5 now. What we need for this is a string or a wire. We need a bench with a pulley. So a bench. This is a bench with a pulley at the end. This wire overlaps it actually. Then we need slotted masses and a hanger. So like this. Then we need a meter rule which we'll place on the bench. And we will need a vibrating or a signal generator here. So over here, put a signal generator that vibrates the wire. And we will need a bridge. The bridge is essentially just a connection here. So it's not necessary, but what we're gonna do is attach one end of the string to the vibrator here, the other one to the pulley like we've drawn here. Attach a mass of, let's say 100 or 50 grams. Let's just use 100 grams, sorry. So the string becomes tight, you know. Then we move the bridge. So the bridge is not actually here. So we move the bridge so that the length of the oscillating section is of the string is 1 meter. So this is what we'll do. We'll put it here. And basically we will the goal of this experiment is to investigate the wave properties, okay? So you investigate the effects of length, tension, and mass per unit length on the frequency. What do we mean by this? This is the wire, and when we move the bridge so that the length of the oscillating section is 1 meter, what do you mean by that? This section here is 1 meter. And then we turn on the vibrating generator and adjust the frequency until a stationary wave is created. What is a stationary wave? This is unit 2 now. A stationary wave is essentially a wave that does not propagate in a certain direction. How do we create a stationary wave? You will send frequencies in one direction, and that will rebound and come in the exact opposite direction, and it will cancel out it'll cause destructive interference and cancel it out. So we're left with a stationary wave, okay? That does, so we draw it like this, you know. Oops. My drawing today is very bad. So we're left with a wave like that. You know, it propagates, but it just, you don't show it, okay? It doesn't actually propagate. Yeah, and you repeat by moving the bridge 10 cm. In this case, the bridge it's a theoretical term. This distance is 1 meter at the start. Then we move the entire signal generator till it's about here, and now we have 90 cm, you know. We keep on doing that, we repeat values, and we find the mean frequency it takes to create a stationary wave, okay? Um, that's how you do it. That's what you do in this experiment. But it's important to note that in the exam, they will not ask you to describe these experiments majorly, especially this experiment. Rather, they will give you an experiment that is happening and they'll tell you to do what you need to do about it, okay? So you plot, for this experiment, you can plot a graph of 1 over frequency, which is also time period, against the length of the wire, okay? You draw a line of best fit. So you're given values like this, you know. So you draw a line of best fit. Remember, line of best fit has to go above and below the same number of points. But here, since the distance here is greater, we'll just put it like that. Um, if you're too stressed about how your line of best fit looks like, don't be stressed. It's just there's a range in the exam as long as you're drawing something that is close to what the answer is, okay? Uh, Anyways, after you plot the line of best fit, you will have a gradient. Your gradient will be equals to 1 over frequency times the length. So this gradient here, draw a large triangle. This is how to improve on accuracy. They can ask you this as well. Draw a large triangle when checking the gradient. Your gradient is equal to change in y over change in x, which is 1 over f divided by L, which is 1 over FL. Yeah, so your gradient, you multiply the gradient by yeah, so essentially this is how it's going to look like. And using the gradient, they can ask you different values. Uh, what is what you need to know for the experiment is safety precautions as well. This we did in our previous video as well. This wire has tendency to break. Due to that, we have to wear safety goggles to prevent the wire snapping and reaching our eye. Also over here, we place a sandpit to cushion this and don't put your legs next to it. Now, since it's your exam, you can put in your own, based on the marking scheme, it's written that you can use your own examples as long as it's valid. An example here is when you are placing the pulley, do not put your fingers too close to the pulley. That is not in the marking scheme, but it is given as an answer in some cases. But whenever you're given these questions, just go for the very common ones like the wire breaking, so wear glasses, safety goggles, and put a sand pit here to catch the falling weights, okay? Again, this experiment is not majorly stressed on, rather the contents of the safety and also the graph drawing is majorly stressed upon. So, core practical 6, determine the wavelength of light from a laser or other light source using a diffraction grating. What is a diffraction grating? It's essentially a grating with many slits in it, okay? Each slit is like a very small hole, okay? So each slit is gonna be like 1 micrometer on 1 micrometer. This is just it's not actual, okay? I'm just drawing my own stuff, but you get the point. It's very small, slitted, okay? So what you need is that the diffraction grating, you're gonna need a laser, and you're gonna place the diffraction grating right in front of it, and you're gonna need a screen or a wall and a ruler, okay? Ruler. Now you'll shoot the laser onto the diffraction grating, and essentially you'll see a pattern form. So you'll get bright dots. So there'll be a bright dot here, 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 okay? Now what you're gonna do is you measure the distance between the central order, which is this 0 order, to the first orders. You measure this distance here, d, okay? It should be equal on the same side. Just in this diagram, it doesn't look equal, but it should be equal. Yeah, so what else you measure is this distance here. Using the ruler, you can measure this distance here from the diffraction grating to the screen. And also, yeah, so now what is the main purpose of this experiment? Well, there's an equation in unit 2, d sine theta is equals to n lambda. D is the distance between the diffraction Uh, yeah, so when you are doing this, just give me a second, guys. Uh, 1 second, guys. Yeah, so when you're given this experiment, you are given this formula majorly that you will use to navigate around. So this formula has D. What is D? D is essentially the distance between the slits. So we did it up here. D is basically this distance, D, okay? Sine theta, what is theta? Theta is the angle here, or it can be the greater angle here, okay? N is the number of orders. In our case, we just did one order, and lambda is the wavelength of the light, okay? Now, you're wondering, how do we get the theta? Do we use a protractor or something? But no, that's why we measure this distance and this distance here. We are going to create a triangle. So this is first order, zero order. That's right angle, and we're going to have theta here. We have D here. We have D here, and we have, let me use a laser light, not use that. Yeah, this distance here, using the measuring ruler, let's make that X, okay? So we have X down here. And then we can use tan theta is equals to opposite over adjacent. Your opposite is D and your adjacent is X. So theta is equals to tan inverse of D over X to get your theta. Yeah. They can ask you to find the wavelength using this formula. They can ask you other stuff. They can ask you what happens when D becomes smaller, what happens when lambda becomes bigger. Essentially, just pause, don't stress. D sine theta is equals to n lambda. Make your own values. Let's put 1, let's put 3, let's put 1, let's put 3. Now let's say, what if this D decrease? So let's put, instead of 1, let's put 0 0.5, and then let's try it again, okay? Yeah, what then you can my example really doesn't make sense in this case, but yeah, whenever given a question like this, just put your own values, then decrease your value and check how the other values compare. In this case, if you lower D and let's say theta and n stay constant, then your lambda, which is that I just dropped by mistake, will also decrease your wavelength of the light, okay? Yeah. So yeah, anything else safety you need to know? Again, very straightforward. You're using a laser. Laser can get into the eye, so where don't look directly into the laser. Another one is that people could be uh, allergic to the laser, so just stay away from the direction of it. Uh, yeah, again, it's a laser and it reflects along surfaces, so make sure the screen is not reflecting. Okay, non-reflecting. That is non-reflecting. I know it's like unreadable. It's very unreadable. But yeah, okay. Um, Next part. So we can take that. We already did that. Now we can take this one as well. So core practical 7 now is electric circuits. Determine the electrical resistivity of a material. Okay. So what do we need for this? Before we begin, what formula is for resistivity? Resistivity is given by Ra over L. Okay. Do not mix this up. When you are trying to see, I used to get mixed up by this. I used to write resistivity is equal to RL over A, but it's very easy to get mixed up with this. How I remember what this is, right and left are always on the opposite sides, and then my name is RA, and then it starts with RA, so I put A. Whenever given questions like this, just try and find tricks to make you remember, and it'll work out very nicely for you, okay? So what is this experiment? Essentially, you need a constant length of wire, let's say 1 meter wire. Let's just draw that here. This is the wire, constant length. Let's put it as 1 meter. You will need a voltmeter. You will need an ammeter, and you will need low power supply. You will need a micrometer and a meter rule. So let's just connect all of this. Remember, ammeter is in series because it doesn't have, yeah, so voltmeter is in parallel. It's all unit 2 stuff. Um, yeah, so what do we do here? Essentially, we measure the distance between the wires at 3 different points. So when you're given a micrometer, let's just imagine this is a micrometer. It doesn't look like a micrometer, but let's just imagine it's a micrometer. There's also how to read a micrometer, which I have done in a previous video. But if you can't find my video, I suggest you look at other YouTubers. Just search how to read a micrometer and the perfect videos will come up. I urge you to look at the 5-minute videos. They're very straight to the point. Now, when you're given a micrometer like this, you will measure the wire at 3 different points and at 3 different angles. So first you'll measure it like this, then you'll measure it like in the horizontal angle, and then you'll measure it straight again or something, at 3 different angles to measure the diameter of the wire. Whatever you get diameter 1 plus diameter 2 plus diameter 3. You will divide it by 3 to get the average diameter. So av d, oops, let's just do d av. Yeah, and that's your average diameter. You set that to the side. So your diameter is equals to d av, okay? Now you set up the experiment as shown here. And in the experiment, if you're asked to do an experiment, if you're asked to say the procedure, you will be allowed to draw an experiment. You'll be able to draw this setup, okay? So adjust the length to around, so this 1 meter wire, we can adjust the length. So let's just put it as 1 meter, okay? And remember, we do not have a switch, so don't write turn on the switch if you've not drawn a switch. That can cost you marks as well. So once you have connected the wire, check the ammeter reading, check the voltmeter reading. This is your current, this is your voltage, and essentially record that somewhere, okay? Yeah, so create a table of not resistance, sorry, of I, of A, and over here you use crocodile clips, which are essentially just clips. You know those clips you used to hang your clothes sometimes, like at the back on the wires you used to hang your clothes. Those are called like crocodile clips, but they're made out of metal, so they conduct electricity. So put the crocodile clips and measure the distance apart from them. Label that as D. Yeah, and then you just, R is equals to V is equals to IR. So V over I is equals to R. Your D, in this case, 1 meter, so 100 cm. Then check the values here, record them down. Move this crocodile clip, put it around here. So it's now 90 cm, that's 90 cm. And then do 90 cm. Get at least 6 values, 80 cm, 70 cm, and 60 cm. And this for 5, so one more 50 cm. Yeah, use your I and A to find your resistance, and essentially you're left with these values, okay? Now, what do? We plot a graph. Actually, we don't even need to do this table. Just for one knowledge, we can do it, okay? But what we need to do is we plot a graph of the mean resistance. Sorry, we do need to plot, yeah, we do need to create this resistance column as well, calculate it, use the I and the A to, use the I and why did I do I and A? This is supposed to be voltage, okay? One is supposed to be the reading on the voltmeter, one is supposed to be the reading on the ammeter. Use those two values. So V, and A is for current, which is I. Use these two values here. Get your values of resistance. Set that aside, okay? Now you plot a graph of the resistance. So these R values against the against length, which is D. Remember, D can be interchanged. Just keep on moving the crocodile clip. So your circuit is only till here. This all, no current passes through it, obviously, okay? So plot a graph, create a line of best fit again, let's say it's like this, go in the middle. Let's say there's one here, move a bit upwards. Let's say there is two up here, move a bit upwards like that. Make sure three are down, three are up, something like that. Your gradient will be equal to, so when you're given this, you essentially have resistivity is equals to RA over L, yeah? What you do is R over L is equals to the gradient in this graph. Remember, R is the change in Y. So R, and then D, change in R over change in D, change in R over change in D is equals to change in Y over change in X, which is equals to the gradient. And M, which is the gradient in this case, is equals to R over L, like we've shown here. Multiply this gradient by the cross-section area we found here, which is now D average. We will do D av over 2 to get the radius average. And how do we find the cross-sectional area of a wire? A wire is essentially a circle. A circle's area, this is the cross-sectional area. It will be equals to pi r squared. We have our average, so our average squared times pi. This is your area, your cross-sectional area, okay? Multiply that area here, and you will essentially get your resistivity. That is how you find the resistivity of the wire. Safety precautions here is when you are when you are recording or when you're calculating, remove the crocodile clips to open the circuit, okay? Because the wires can heat up and that may affect resistance of the circuit. I can't stress this enough. That is most likely they can ask that tomorrow. They always ask it in most of the past papers, okay? Next up, just be careful under the electrical equipment. That's why we use a low voltage battery. So yeah, what we're supposed to know is that. Yeah, that's for that core practical. Core practical 8 now. Determine the EMF and internal resistance. This is the last core practical. So core practical 8. What do we need? We need a battery or a cell. Let's just have a cell. We need a voltmeter. Let's have a voltmeter here. We need a ammeter. Have an ammeter here. We need a variable resistor here. Oops. Variable resistor, and we need a switch. Complete the circuit. Yeah. Now set up that apparatus as shown above. Essentially, when you're told to write the procedure, you draw and then you say set up the experiment as shown above. Then you set up the variable resistor, which is this component, to its minimum, maximum value. Okay. Variable resistance is able to change in resistance, which can be used to control the amount of current in the circuit. Now, we close the switch and we record the voltage from the voltmeter and the current from the ammeter. Then we open the switch between readings. Again, why do we do this? It is to prevent heating of the wires, which would affect the resistance of the wires. We should change the values, okay? Remember, if wires are more heated, the resistance will be affected, and if the resistance is changed, it will cause the current to change as well, okay? Now, what are we supposed to know from this experiment? So you read those values and you decrease the resistance of the variable resistor as you move on, and you collect the values for V and I again and again, okay? That's what you do. Essentially, you're going to be left with V and I, and you're gonna get at least 6 values again. Now, calculations. What are you supposed to do for the calculations? Um, so internal resistance is given by the formula E is equals to I R plus R. R is the resistance, the main resistance, and the small r is the resistance of it's the internal resistance. E is the EMF, and the small r is the internal resistance. What is internal resistance? Is essentially the resistance inside the battery or the cell. Now, yeah, so when we extend this, we get E is equals to IR plus IR. Remember, V is equals to IR, so E is based, so we substitute this here, and we get E is equals to V plus IR. Now, we have values of V, we have values of I. This coincidentally looks like, let's just draw it better. This coincidentally looks like this, which is Y is equals to MX plus C. Yeah, so so this is how it's gonna look like. But you're supposed to change this around to make it in the form. Remember, your EMF is a constant, and your R is a constant. Your R is with another value, meaning, and let's just look below here. M is a constant and C is a constant. M is with another value, so M and R are together. E is alone and it's a constant, and C is alone and it's a constant, so we put that together. So let's just write it better. Y is equal to mx plus c. We have our c, which is E. We have our m, which is R. And I is also similar to x now because it is with R and x is with m. So I here. And yeah, what else is left? V. V is left. So we take V to the other side. And essentially, instead of taking V to the other side, we will, when you are making V the subject of the formula, now we know to make V the subject of the formula here, okay? So E is equals to V plus IR. We will make V the subject of the formula and we get V is equals to E minus, when we take this other side, it becomes minus IR. So let's make this into the form of here. Remember your R is the gradient and your E is the C. So we will write that as V is equals to negative RI plus V, okay? Sorry, plus E. Yeah, so we have y is equals to mx plus c graph here. Your m, which is the gradient, is equals to negative r. Your y-intercept, which is c, is equals to the EMF, okay? We have our values of y and x, which is v and I, which is gotten by this table here, that we found out. And essentially what's going to happen is we draw a graph of v against I, and whatever line we get here, the gradient is equals to negative, so m is equals to negative r. So let's say we get negative 5, that'll be equal to negative r. So r internal resistance will be equal to 5 ohms, okay? Your y-intercept here will be equals to your E, okay? That's it for this experiment. It's a pretty straightforward experiment, but one of the risks is avoid using high voltages in your circuits because it can cause electrocution. Also, calibrate the ammeter and the voltmeter. This is very important for your exam tomorrow. What does calibration mean? It means that when you're make sure that when there is no current flowing through it, the reading is 0, so that when there is current flowing through it, you get the accurate reading. And let's say when there is no current flowing, the reading is 1 volt, and when there is current flowing, we get 6 volts. So you subtract 6 minus 1 to get 5 volts, which is caused by the circuit alone. Okay, similar for the ammeter, you do that. Yeah, that's all we need to know for this. Now, yeah, is there any more core practicals? No. Okay. Another thing I'd suggest for your exam tomorrow Just be confident in your answers. Remember, it's a unit 3, so whatever answer you give will work out. Also, if you're looking at grade boundaries, I suggest you don't do that till after the exam, as the hardness, if that's a word, of your exam will determine the grade boundaries, okay? When I was doing my exams last year, the grade boundaries were insanely high, but my exam was a bit on the hard side, so the grade boundaries came low, okay? Um, Also, I suggest you look at other videos as well, like how to read a micrometer screw gauge and how to read the other measuring instruments, and just be confident in your responses when you are doing the safeties. You know, if you think something is right, write it down. It most likely will be given, okay? But yeah, if you revisit tomorrow, good luck. If you see this in the future, also good luck. That's it for this video.